This course is about groups, and in order to know what a group is, we first need to know what a binary operation is. Informally, a group is a set paired with a well-behaved operation. For the moment, we're going to be silent about what is meant specifically by well-behaved. Through the semester, we're going to see many examples of groups. Here are 3 examples. The first one is an example that you're very familiar with. It's the collection of integers together with the ordinary operation of addition. If you take 2 integers, 5 and 7, and you add them together, you get a third integer, 12. The other 2 examples are ones that you're probably not as familiar with. So the second example, we start with a set. Actually, it's a finite set, and we consider the set of all subsets of that set. And the operation is going to be this symmetric difference operation on sets. So that example was described in your reading. The third example is the set of symmetries of an equilateral triangle, where the operation is just function composition of symmetries. This is an example that's going to be described in your reading, and it is also described in the video that I posted on symmetries of the triangle. Now, the thing that you might notice about these examples is that they seem very different superficially. I mean, the integers under addition seems very different from the set of symmetries of an equilateral triangle under function composition. Yet both of those examples, in fact all 3 of these examples, are groups. Now, before we go on to try to describe explicitly what is meant by a well-behaved operation, I want to say one thing that we absolutely need to have to be true in any group. So the very simplest type of equation that we can have in a group would be something like A star x equals B. So A and B are known elements of our group and x is unknown. And one thing we want to be able to do always is to solve an equation like this for x and obtain a unique solution. All right, so we must have a unique solution. So that's our first indication of one thing that we mean by having a well-behaved operation. So here we have the formal definition of a group, where we're told explicitly what it means for this operation to be well-behaved. The desirable properties of this operation are encoded in these 3 properties that you see in the bullet points. And in the future, we're going to be talking quite a bit about those 3 bullet point properties of the operation. But the first thing that I want you to focus your attention on is these 2 words, binary operation. So apparently, in order to understand these 3 bullet points, the first thing that we need to do is know what a binary operation is, and that is the subject of this video. A binary operation on a set S is a function that takes an ordered pair of elements from S and returns an element of S. Now, there are lots of examples of binary operations. The first one here is one that you've been familiar with for a long time. It's just ordinary multiplication on the set of real numbers. If you take 2 real numbers and multiply them together, you obtain a third real number. The same is true of division on the set of non-zero real numbers. If you take 2 non-zero real numbers and divide them, you will obtain a third non-zero real number. Matrix multiplication is a binary operation on the set of 2 by 2 matrices with integer entries. So if you can imagine, 2 such matrices, if you multiply them together, you get a third. matrix, 2 by 2 matrix with integer entries, and also set complementation on any power set is a binary operation. Now, one thing that we need to be careful about with binary operations is to understand that the order that the operation occurs may matter. For instance, S1 star S2 and S2 star S1 may not give the same result. So maybe the easiest way to see that from our examples is to look at, say, division, right? If we take 3 divided by 2, and we take 2 divided by 3, those are different, those yield different results. Now, order will also matter for matrix multiplication and this set complementation operation. And in fact, why don't we look at an example with the set complementation operation, because that is an operation that you may not be really familiar with. So how do we do that? Well, we first need to start with 2 subsets of the set 0, 1, 2. So for instance, let's let A be the set consisting of 0 and 1, and we'll let B be the set consisting of 1 and 2. Now, when we take A minus B, what are we doing? Well, we're just identifying everything in A that is not in B. So there's only one thing in A that's not in B, and that's 0. So it's the set 0. That's the difference, the set difference, A minus B. Now we could also do B minus A. So here we're now looking for everything in B that's not in A, and that would just be 1. And notice that A minus B and B minus A give different results, so order really does matter. Now for multiplication, our very first example that we talked about here, for multiplication on the real numbers, order does not matter. You know, if you take 2 times 3, you get the same result as 3 times 2. However, we just need to keep in mind that for binary operations, it's not a given that, that you can multiply things in any order. Sometimes binary operations can have additional desirable properties. The first of these is one that we were just discussing a moment ago, and that is sometimes the order in which the multiplications occur does not affect the outcome. That is, S1 star S2 and S2 star S1 give the same result. So whenever that happens, we say that the operation, the binary operation, is commutative. On the other hand, sometimes you have a binary operation where the grouping of a product doesn't affect the outcome. So when that happens, we say that the operation is associative. So here below now we have several examples. So the first is just the ordinary real numbers with binary operation multiplication. And that we know from long experience is both commutative and associative. You know, multiplication on the real numbers doesn't matter what order you multiply in, and the groupings that you form in a multiplication don't affect the outcome. So now if we move from multiplication on real numbers to multiplication on matrices, we keep the associativity, but the commutativity no longer works, right? You might remember from linear algebra that matrix A times matrix B may not yield the same result as matrix B times matrix A. So then moving on to the integers under subtraction. So this is a very, very poorly behaved binary operation. Subtraction is. It's neither commutative nor associative. So now a little challenge for you. I'm wondering if you can think of a binary operation on a set that is commutative but not associative. So I'll let you, maybe you want to pause for a moment and think about that. Okay, well, you've probably in the interim, thought of lots of good examples. Here's one that I came up with. So we can just look at the integers under an operation star, where what we're going to do is have a star b be equal to the absolute value of a minus b. Okay, so the first thing to do is to check that this is a legitimate binary operation. And indeed it is, right? Because if we take any two integers a and b, we can subtract them to obtain another integer, and then we can take the absolute value, and we still get an integer as a result. Now, one thing we might notice about this is that absolute value of a minus b is the same as absolute value of b minus a, but that's just b star a. And so the operation here is commutative. However, it fails to be associative. For instance, if you were to take 2 star, and now we're going to have the grouping minus 2 star minus 2, I claim that that is different from what you would get if you grouped it like this, having 2 star minus 2 and then star minus 2. Okay, so let's see what we get on the left and the right and check that they really are different. So the thing on the left, I believe, is this. It's just absolute of 2 minus the absolute value of minus 2. And then we're taking a minus 2, which is, well, that's just a plus 2. Whereas on the right, we're taking an absolute value of absolute 2 minus 2, which would be 2 plus 2. And then minus 2. Okay, so on the left, what happens? Well, on the left, we get 2, and on the right, what do we get? Well, we get 4, we get 6, actually, on the right. So indeed, the grouping does matter here, and so this operation fails to be associative. So sometimes there are operations on sets that kind of look like binary operations, but they aren't really binary operations. And so the main way that an operation can fail to be binary is where you take two things in the set, two elements of the set, and you multiply them under the binary operation. And it gives you something that lives outside the set, okay? So prime example here would be the positive integers under subtraction, right? So many times it's true that if you take two positive integers and subtract them, you get a third positive integer, but it doesn't always happen like that, as you know, right? I mean, you can take 2 minus 3 and get minus 1, and minus 1 is not an element of the positive integers, right? So this operation is not binary. So a similar thing happens in the second example. Here we have this set and this sort of funny-looking operation where a star b is just going to be the absolute value of b, And again, many times when we multiply things together in S under this operation, we get a third element of S, which is all fine and good, but it doesn't always happen like that, right? So for instance, if we were to take 3 star minus 4, well, that tells me that I'm to take the absolute value of minus 4 as my result, and that just gives me 4. But if I look in the set S, I don't see 4 as an element. So 4 isn't in S, and therefore this operation is not binary. Well, and a very similar thing happens in the third example. Here we've just got the collection of integers with this proposed operation where we take a times b on the top and a squared plus b squared on the bottom. And, you know, there's lots of ways that this fails, right? Because for many integers a and b, this quotient is not even going to be an integer. And sometimes, like for instance, if a and b are both 0, then the quotient isn't even defined, okay? So I guess the main point here is that, you know, not every operation on a set should be automatically judged to be binary. You have to think a little bit. There might be some checking that's needed to be sure that every pair of objects in the set S multiplies together to give a single third object in the set S.